get it started. Good morning and good afternoon, depending on where you're joining us from today. Leading our talk on spray basics and how understanding these can lead to innovation will be Regional Spray Specialist Justin Berger and PhD Research Engineer Kyle Bade. They'll be leading us through some spray nozzle basics, spray patterns, applications of interest, and then how understanding all this can help you lead to innovation in your industry. Throughout the talk, please send questions either through the Q&A or through the chat, and the guys are more than happy to be interrupted with these, so we'll answer questions live and on spot as you answer them. All right, take it away, guys.
Yeah, thanks, Mary. Appreciate you setting this up for us. And so what we're going to look at today are just the basics of spray nozzles. So Mary, you can get us on the next slide. And what we're going to see is drop size, the implications that might have on your spray application, as well as spray pattern and type, your spray angle, velocity, and also spray impact. And what you're going to see throughout this process and this presentation is the folks who have the data of this type of information are the ones who win with various applications. The more data that we're able to capture, the more understanding we get, and then that leads to competitive advantages or deeper insights to various processes. Next slide. And before we get into really the drop size piece and the details, it's just understanding how a spray forms and those stages. If you've ever played with your faucet, for example, as you increase that pressure, certain things happen, and you can notice that just in your own kitchen sink that there are different characteristics from that. You start with the dribbling stage all the way to a fully developed spray. And Kyle, can you kind of share what we're looking at here within this imagery and what the various stages are and what impact that might have for different processes?
All right, thanks, Justin. Yeah, so these images show what I think is a great starting point where as the pressure from a hydraulic nozzle is increased, so as you can see in the far right, eventually at a high enough pressure, you're going to have a fully atomized hollow cone spray pattern. But at lower pressures, if we start on the left, you'll see dribbling and big droplets, inconsistent. It's not fanned out or really spraying, it's just dripping. And then as the pressure is increased, you can see that pattern start to fan out. It starts to become a bit hollow, although the surface tension of the water is collapsing the liquid back in. So you're still not getting much of a distribution of the liquid, and you're going to have larger droplets, as you can see at the bottom of those images. When we get into this sort of tulip stage or the fully developed spray, you start to see that the spray is no longer collapsing back in on itself. It's starting to spread out, and you can just visually even see that the droplets are smaller. You don't have these big chunky ligaments and larger droplets existing still. And then in the fully developed spray on the far right, again, there we have a spray that's aggressively atomizing and breaking up into smaller droplets. You can even see some regular sort of surface waves of the pattern because you have the liquid really being ejected from the nozzle in an intentional and fully developed way.
And Kyle, you know, we get to have the privilege of being out in the field and this development progression, if you will, from low pressure to a bit higher pressure. And oftentimes I deal in the oil and gas industry, petrochemical, and we're injecting into a pipe. And typically those pipes are under pressure and there might be vacillations of that pipe pressure. Can you describe what happens when that delta P, you know, in our minds, we might be expecting a fully developed spray pattern, but let's say that the pressure to the nozzle is staying the same, but the pressure of the vessel that I'm spraying into increases. What can happen in there, and what have you seen from a lab perspective?
Yeah, absolutely. So the delta P across the nozzle, so the pressure upstream of the orifice to the pressure into the environment you're spraying into, is going to be what we call the operating pressure of the nozzle. And so that's most critical. Now, as the environment pressure goes up, your delta P then goes down. So you're going to start to revert back to stages potentially on the left-hand side, right? Which isn't what you really want. Additionally, as pressure goes up, if you're dealing with something, a compressible gas or something that's spraying around the nozzle, the density of the environment goes up, and you'll have a more aggressive breakup of the spray. You can imagine there's much more drag and resistance to the fluid as it tries to leave the nozzle and expand out into the environment. So you can have some, at higher operating or environmental pressures, you can have a little bit more atomization and slower velocities. You can think of that as a drag effect in the environment. But if you have something that's atomizing well, you typically aren't going to see that. The fluid, whether it's say it's water or an oil, is so much heavier than the gas that density would really have to increase a lot to make a real appreciable effect.
And Kyle, you mentioned something pretty important. The characteristics of the gas or atmosphere we're spraying into can have an impact, particularly on certain applications, but also this dribble piece down on the far left-hand side. Imagine that big glob traveling at high velocity and hitting a turn in a gas stream. Not only the erosive effects that might have, but also the opportunity for depositing and corrosion as well. And I think that this visualization is very powerful, for these process industry type folks. Yeah, thanks for that, Kyle. Next slide, Mary.
Before we move on, we have a good question from one of our attendees. For this particular visual, why did we select a hollow cone nozzle?
Great question, Kyle. I'll let you kind of field that one.
I can answer that. I think it's one of the more interesting hydraulic sprays. So an air atomized spray, you can't see what the air is really doing. So having a hydraulic spray is a nice selection to visualize this process. And a hollow cone provides that obviously a thinned out center. So we've got this liquid sheet forming on the far right-hand side. And I think that goes a long way towards showing not only a liquid core leaving the nozzle, this sheet leaving the nozzle, but then atomizing into first some ligaments. If you look at maybe in the middle of that image, you can see some long strings or strands that the liquid is starting to break up, but it's not yet droplets, and eventually becoming droplets. So it's a nice way to visualize the spray, whereas a flat spray, you would have a similar process, but you can't sort of visualize the three-dimensionality of the spray as much. And a full cone spray, there's so much happening across the spray pattern that it's harder to visualize as well.
That's great, thank you.
So it's a jumping off point. Yeah. And we'll see a lot more of different types of sprays in the presentation. Yeah.
Yeah, this next question leads really well into our next slide. Is this process the same regardless of the fluid being sprayed? So I'll kind of go into the next slide and you guys can answer this a little bit.
Yeah, that's a terrific question. And so on the next slide, you'll see a number of environmental factors that can really impact the sprayability of what you're working with. You have specific gravity, you have viscosity, surface tension, temperature, and then too, we mentioned a little bit about that abrasion and corrosion implications. And your specific gravity goes into how much liquid you can spray, how dense is the liquid. In the lab, we get to play a lot with water, but in the field, that can have a dramatic effect on how your flowability would be for your spray. And then Kyle, I'll let you speak a bit to the viscosity. We're able to spray anything from water to peanut butter, right? But the approach to that viscosity difference is very important. So Kyle, what's your experience on the viscosity of liquids and that sprayability?
Right, so viscosity and surface tension are probably the most relevant parameters here. The temperature itself does not change the spray pattern, but it will have an effect on density, surface tension, and viscosity, right? So temperature certainly is important. And, a lot of times if we have a high viscosity spray where it doesn't really want to flow, it doesn't want to atomize, by increasing the temperature of the liquid, we can bring the viscosity down and promote atomization as the spray leaves the nozzle. So viscosity is most often the critical parameter we're looking at if you have a higher, if you have a higher viscosity spray, and how can we spray this, what nozzles are we going to use? If we're trying with a hydraulic nozzle, we're going to have to either add temperature to bring the viscosity down or add pressure to create, put more energy into the liquid to promote atomization as it leaves the nozzle. Or if we're using air atomizing or another technology, then we can turn those knobs as well to try to overcome the viscosity effects of holding that material together, basically, is what's happening. Abrasion, corrosion, again, that may affect the nozzle. material, it may affect the surface you're spraying onto, but it's not necessarily directly going to have an effect on atomization, but certainly important.
Yeah, and Kyle, on you mentioned viscosity and temperature, and really how important it is. The viscosity is what it is, but that temperature can reduce or adjust that that parameter. And one application I'm familiar with and reminded of is a mold release, and our particular client was having issues with misting. And one thing that we found fascinating was they were measuring temperature way up high somewhere, quite a bit away. And whenever the liquid got its way to the nozzle, the temperature changed by about 5 to 10 degrees. And that 5 to 10 degree difference had a massive effect on the viscosity, which then went into impacting the amount of misting of the oil, and it created a large health and safety challenge throughout the plant. And so these parameters, while simplistic in nature, can have massive impact on your process. And two, on that atomization and how much energy is required. Like Kyle said, the amount of energy to atomize it, you want to do that, but also you want to look at your transfer efficiency. And those are some of the aspects of that spray pattern that are very, very important for various applications. Next slide, Mary.
Yeah, and one of the things we can do, Justin, just to touch on that is not only measure or look at how a material might spray with a nozzle, but we can also generate, say, a temperature viscosity curve for material, right? So you might hit some critical point where if we could just have 5-10 more degrees temperature increase, like you say, something's going to spray a lot easier because the viscosity curve is really falling across that temperature range.
Yeah, there's a critical point. And what we've observed in the lab and in the field is the impact that viscosity, temperature and viscosity together, right, have on spray pattern. And then you talk about transfer efficiency, then you have misting and all of these unique things that happen when you collapse that spray pattern. It's a lot of opportunities for optimization with the more information.
Yeah, surface tension is just a little bit different. Typically, we find that the surface tension of a material does not change in a more gradual way like viscosity. And so with surface tension, you might think a material is going to spray and it doesn't for some reason. And sometimes you can point to the surface tension for that. And if you can just overcome, increase the pressure a little bit more, you'll find that spray that will not atomize nearly at all will all of a sudden burst into a fine spray based on its surface tension. So, balancing these different parameters is something we do in the lab all the time, and we do our best to try to identify which rheology characteristic is leading to maybe a poor or underperforming spray, and how to turn the right knobs to find an atomized spray.
Yeah, that's fascinating. Thank you, Kyle.
All right, we got one more question coming in here too. Do you have more mist in lower temperatures?
Yeah, Kyle, I'll let you go to that. It depends on the rheology, but Kyle, I'm sure
it's very dependent. The type of, what are the material properties of the material, and then what type of atomization technology are you looking at? We're gonna touch on some hydraulic sprays. We're using a pressure-based atomization, but then you can have air atomizing sprays, which tend to make more finer droplets. Someone else is bringing up electrostatics, ultrasonics, different technologies. So it's really dependent. Typically, lower temperatures, you're going to have a higher viscosity, and in that case, the spray droplets or the liquid material will tend to stay together as it leaves the nozzle, and so you end up with larger droplets.
Great, thanks, guys.
We'll get to the electrostatics in I think a few slides here. So if we can hold that question, we'll get back to it.
Yep. Okay, so as you can see, there's a number of different sprays and nozzles that we can look at, and most applications have their own unique requirements and specifications. It's very important that we select the best nozzle for your application, but also take into account all of those environmental concerns on how the rheology would be impacted with what you're trying to achieve. Next slide. So we mentioned a couple of different spray nozzle types. Really, there's three main types that we're looking at. You have your hydraulic, which is just strictly pressure. You also have your pneumatic atomizers, which are two fluid type nozzles. And then we have the fun ones, which are ultrasonic and electrostatic. So we're going to look at those three different types of classes of nozzles, and then we'll kind of explain what the pros and cons and the advantages are of each one. So you can see our spray pattern types. We go all the way from a solid stream to a flat fan, to a hollow cone, down to our full cone, hydraulic atomizing, and fine spray. And that solid stream is an interesting concept because it does supply you with a good amount of impact, but only over a certain distance or certain time. On our next slide, you're going to actually see that we can keep that intact, but there's also a good amount of high impact, and we use those in a lot of tank cleaning applications where you're looking to use that spray to either remove various particles or various pieces of debris. But what's fascinating, on the next slide, you'll see with that solid stream nozzle that over a certain amount of distance, it actually starts to break up and you get a certain amount of wetting at the end. And Kyle, can you describe just the way that impact ratio occurs, right, between that solid stream, which is really high impact, good for cleaning, and to that transition of rinsing versus wetting?
Yeah, so the impact force is obviously a function of the mass of the spray as well as the velocity of the spray. And the mass sort of plays in with the spray pattern type. So as you can see in the drawing here, you've got a solid stream for some distance, assuming we're spraying horizontal here. The spray might tend to break up and form more of an atomized or distributed pattern. And once that happens, you have less mass hitting each area, and the velocity will inherently start to slow down and maybe be directed more downwards as gravity takes effect. So you can see if you really wanted the highest impact, you'd want to be closer to the nozzle as close as possible for a high velocity and a smaller spray pattern, right? And then as you move away, the spray is going to slow down and spread out, so you're going to have less of an impact. So if you're trying to do something like a descale process where you need to remove a material over a larger area, then you might go to a fan spray or flat spray with still a narrow angle, so you have a high impact. Or if you're trying to clean something like a tank, you really usually can't get away with a more static nozzle setup, so you'd have to go with a rotating nozzle. So we make these types of sprays as well, where the patterns themselves, the solid streams, move around through the tank to perform the cleaning within the entire 3D geometry. And I think towards the end of the presentation, we do have a little video of something like that happening.
Yeah, and Kyle, the critical piece on the solid stream nozzles is understanding what your goal is and how to leverage the physics behind what's happening, like you said, for debris removal or a descale closer in. However, if you want to get some good wetting and good coverage, you can position that nozzle a bit away and get some good rinsing effect with the solid stream nozzle, while maintaining a certain level of that energy versus just using a flat fan. So
yeah, that's a great point. The cleaning, rinsing, wetting idea. Yeah, that makes a big difference if you're trying to clean something that's really stuck on versus you just need the water to rinse off the surface or even just fall onto a surface. Yeah.
Yeah, thanks, Kyle. Mary, next slide. So the next type of nozzle that we have are the flat spray fan nozzles, and those are pretty fascinating whenever you look at it. And what we have to the right is a distribution, and that distribution is showing you the amount of liquid from the center of the spray and what's being collected. And Kyle, can you describe here what we're seeing specifically on that graph?
Yeah, flat patterns are typically preferred in sort of conveyorized applications or spray boom or something where the target is moving or the nozzle is moving over a surface, right? And so you don't care as much about what that 2D distribution is, but you care what the 1D distribution is, where everything is collapsed in the minor direction of the flat spray. And so what you see in the plot here is a volume distribution in 1D. So this is the distribution of volume you'd see across a conveyor that might be swept underneath the nozzle. And on the left-hand side, you see two different categories. an even spray and a tapered spray, and then a deflected. But the even and tapered, an even spray, if you're going to try to use a single nozzle for coverage, you want a more flat topped 1D distribution, right? And so that's designed to achieve that a little bit better. Whereas with the tapered spray, the gradients near the edges of the spray pattern, like you see here, allow a much more forgiving overlap pattern between multiple nozzles.
Yeah, Kyle, that's a great point. And on the even spray, you can actually see these types of nozzles in use on all the striping, if you will, on all the roads for the center lines. That's an even spray. You're trying to get a nice tight distribution with little feathering at the end, whereas the tapered spray is great for overlapping numerous nozzles to extend your coverage and keep that distribution relatively stable with numerous nozzles. And then on the next slide, what you're going to see is some unique ability to visualize one of these types of sprays with our Spray Scan MPT. And you notice that even though that spray distribution is relatively tight, it still dances, and there's still some type of variance, and that ability to see that and conceptualize that is very, very powerful. And on the next slide, what you'll see is how we can take that and turn it into some valuable insights. So from that Spray Scan MPT, the visual effects, now we're creating a heat map. And with that heat map, we can gain some pretty cool pieces of data. And Kyle, can you describe a bit of that data that we are able to collect and what that might mean for the client?
Yeah, you can imagine whether it's a hydraulic spray or more importantly, like with an air atomized spray, we had this air moving along with the liquid. You can't necessarily collect this type of a spray pattern in a trough or in a collection tube because the air is going to move those droplets around. And so laser sheet imaging, like you see here, is something we use to assess the 2D spray pattern as well as create a 1D spray pattern as well. And Mary, if you want to advance one more, we've developed tools to take those data from a single nozzle and virtually overlap the results to find an optimized solution. So as you can see with the different overlays, we're going to change the spray distance there, and the 1D distribution on the bottom of those plots is much better. Here we can artificially rotate an edge spray so that we have a slightly different pattern, so we can have a sharper edge. Say you have a long conveyor, a lot of sprays in the center that are all oriented the same way, but the one at the edge needs to be a little bit different to have a sharper edge and have a lot of overspray or more of a gradient there. So this software package is something we've developed that allows us to do a lot of different interesting things for our clients to optimize their spray processes and find them the best nozzle without spraying a lot of material, trying a lot of different nozzles. We can do all that in our research facility.
Yeah, and we're even to a point where you can quantify that, right, with the coefficient of variation from, let's say, a new nozzle, and we can start understanding what happens to a nozzle over time to help mitigate some of that energy that we're using to create that spray. And we'll talk a little bit more about that later on in the presentation. And so that was a flat fan distribution. What we're going to look at next is actually a full cone nozzle. Oh, I'm sorry, a hollow cone nozzle, and what that looks like on the Spray Scan MPT. And what's unique about it is you see again that dancing, right, between that pressure. And while this is a very healthy spray pattern, there's the ability to capture what that variance looks like. And so we have the standard hollow cone. We also have a deflected hollow cone, and then a spiral jet, which actually that spiral nozzle is fascinating in that it's creating laminar sheets off of those sharp edges there. And Kyle, can you describe a bit of the dynamics on that spiral jet nozzle, which is very unique to that hollow cone distribution?
Yeah, so the way the hollow cone works is, this is not a precision spray, right? This is a chunky spray that's designed to reliably atomize and break up the liquid. Typically operating at lower pressures, and imagine a liquid core coming through that nozzle, and the spiral actually shaves off the outer edges of that liquid core until it's left with nothing left at the bottom. And so you end up with this spiral pattern. Whatever you're spraying onto, typically larger droplet size, but the the passageway through the nozzle is much larger than any of these other options, which require more of a pressure-driven atomization. So if you have a dirty water source or something that can't fail, or you just need to throw water in some direction, this is something that can accomplish that. Whereas what we call a standard in the top here has a much more engineered whirling chamber inside of the nozzle to pre-film the liquid inside, and then as it leaves the nozzle, it's already a thin sheet that atomizes much more efficiently.
Yeah, and Kyle, can you describe the distribution in your experience, the difference between, let's say, a hollow cone nozzle from, our standard down to the spiral, but also from a hollow cone to, let's say, a full cone, if you were trying to achieve a certain drop size with a certain type of nozzle?
Yeah, the hollow cones, like I described inside the standard nozzle, the hollow cones really pre-film the liquid, and so instead of a liquid jet leaving the nozzle that then has to break up either well or not so well, the pre-filming makes the liquid much thinner to begin with, and so when it goes to atomize, you get smaller droplets. So hollow cone nozzles typically have much smaller droplets than a full cone nozzle.
Yeah, and that hollow cone application might be good for gas conditioning or other types of applications where you need small drop size and high surface area gas interaction.
Right.
Yeah.
Right.
And so what we'll look at next on this imagery is that full cone spray pattern. And Kyle, as we gonna go from the top, from a standard to our spiral, can you describe what we might see from a characterization standpoint with that spray pattern?
Yeah, the full cone nozzles are designed to still spin the fluid and send it out the nozzle at a higher velocity. You can imagine inside of the nozzle, if you just have a liquid core coming through, shooting straight to the orifice, you're not going to spread the fluid out very much, and you only have an axial velocity to help you break up using drag forces as it leaves the nozzle. If you spin the fluid inside the nozzle, you now have an axial and a radial velocity, so your overall velocity is higher when it leaves, leading to better atomization. Also, that spinning of the fluid causes it to follow the exit orifice contour a little bit better and fan out that spray pattern a little bit more. You can see the wide angle there has a sort of a bell-shaped mouth as opposed to just a straight orifice of the standard. The square spray has some wider corners, which allows the spray to fan out a little bit more in those corner areas. And then the spiral jet works the same way as the hollow cone spiral jet. It's just at the very bottom has a little bit of an opening, so it can fill in the center, as opposed to being fully covered up like the hollow cone. A little hard to describe, but there's just a slight difference there. It's the same concept.
Yeah, and on those spiral jets, Bernoulli does some pretty unique things with those spiral jets that we can talk on a later webinar. But Kyle, can you describe too, between the standard and the wide angle, what happens to our drop size in general between a wide angle and a standard?
Yeah, again, like I described with the hollow cone, anytime you can thin the fluid out a little bit more before you ask it to atomize, you're going to have smaller droplets. And so a wider spray angle, regardless of the nozzle type, would typically lead to for hydraulic nozzles, will typically lead to a smaller droplet size, just because you've pre-filmed or pre-spread out that material a little bit to help it atomize once the drag forces take over.
Yeah, no, that's perfect. Thank you, Kyle. And the last piece on the hydraulic nozzle is we're looking at a fine mist on the next slide here. And
hold on, before we move on, we got another question coming in. How would a hollow cone compare to a spinning disc applicator?
Yeah, so spinning disc atomizers typically have, you can imagine a liquid feed at the center of a disc or a cone, and the fluid then flows down towards the edges of the cone or disc that's spinning, and a lot of times you'll have little teeth on the end. And so droplets will then be thrown off of each of those teeth, typically with larger drop size and also a pretty consistent drop size as well from a spinning disc atomizer. However, while the coverage is more, there can be some difficulties obviously with buildup on the surface of a disc. You have this mechanical process happening by physically moving the disc, whereas all these other designs don't necessarily have something moving. So there's things to consider there with complexity of the solution and what can go wrong there. So yeah, there's certainly some differences, but a spinning disc can provide, like I say, larger droplets, wider pattern, and a very consistent droplet size. But typically, so to go back to the question, a hollow cone I would expect to have a smaller droplet size typically.
So the next one is our fine mist and atomizing hydraulic nozzles. And these are very unique in the fact that they use higher pressure and they can produce very small, fine droplets. I believe our HP fog jets can get down to, Kyle, what, about 20 mics or so-ish?
Yeah.
20 to 50. And
or less, certainly less, depending if you're talking averages or maximum. Or
yeah, depending on to your pressures and what you're running it at.
Mm-hmm.
And what's unique about these hollow cone nozzles is at the exit, it is in fact a hollow cone, but over time, or as the distance increases, it gets to be more like a full cone coverage pattern. Just the way that the air dynamics work and those types of physics that are happening. And Kyle, can you describe in the lab, where that fine that fine cone spray nozzle might be a great application, even though from a coverage standpoint, right? So even though it's considered a hollow cone nozzle, how do we get that full cone effect at a farther distance from like a gas conditioning side of things?
Yeah, you can imagine after droplets, especially if they're small, after they leave the nozzle, even if they form into a hollow cone, they're going to start to disperse and move around just due to the air turbulence, either from the nozzle, from the process gas, or themselves just mixing up the surrounding environment, right? And so you typically downstream of the nozzle see more of a full cone or filled in pattern, even if it is a hollow cone fine spray. But these nozzles are designed to operate at much higher pressures to allow you to use the energy within that liquid to generate smaller droplets.
Yeah, thank you, Kyle. And so the next piece that we're going to transition to are our two fluid nozzles. So we looked at
Justin. I think I see one other question too about hydraulic sprays. So
great,
Mary.
Yeah, we got what range of pressure are you supplying these atomizing hydraulic nozzles with?
I mean, it depends on the nozzle type and the goal in terms of the flow rate, coverage, and the droplet size. But the typical operating pressures for a standard hydraulic nozzle would be maybe between 10 and 100 psi. The fine mist sprays can go up into the thousands of psi. And again, it depends on the coverage pattern you're after. More higher pressures, larger flows will tend to spread out more if that's what the nozzle is designed to do. Higher pressures also have more impact. Higher pressures have more energy, can cause smaller droplets. Sometimes you want big droplets, sometimes you want small droplets. So it really depends what you're after. But those are some ranges anyway.
That 10 to 100 range, some of our larger capacity nozzles can still form a pattern down to, 3 PSI. However, that can be very large flows as well, but it definitely depends on the application. Yeah, that's a great question.
Yeah, kind of on that same line of thinking, how much hydraulic pressure do you think is required to fully atomize a Newtonian fluid at water-like viscosity?
Yeah, everything that unless we're noting otherwise, we're sort of referring to water-like setups. This is what we can test with non-water materials in our research lab, but typically we characterize everything in our catalogs and everything with water. So the same rule applies. Like Justin said, it can go down maybe as low as 3 psi and still get a spray. Typically, you want like at least 10 to 40 psi and 100 psi if you're looking at a little bit larger pressures. And there's nothing special about a 100 psi cutoff, right? Like 200 psi, 300 psi. It's depending on what you're after, which nozzle you're using. There could be benefits to that. And then the higher pressure nozzles, again, with water, you might be looking at a few thousand psi. If you go to something that's more viscous, you might need to go up to 10,000 psi or switch technologies, like we're going to go in the next few slides to try to atomize a material that otherwise would not atomize.
Yeah, that's really good. Along that same line of thinking, so after you get the spray atomized, is there a way to estimate the amount of volume displaced based on the liquid you're using?
I might need clarification on volume displaced. The flow rate leaving the nozzle, I don't think that's what you're after, but if it is, it's, you can measure that upstream of the nozzle, right? And that's typically what we would do, is to measure the flow rate going through the upstream supply piping. Volume displaced, I think I would need clarification. So if you want to update the question or add something to the chat, we'll get back to it.
Sounds good.
So we talked a bit about our hydraulic. Now we're getting into our two fluid nozzles, and this is where it gets really neat on your controllability of a spray pattern. And of our two fluid nozzles, which utilize a liquid and a gas for atomization, you have your internal mix and you have your external mix nozzles. So on the internal mix nozzle, you have the liquid and the air cap, and they meet inside of one another. And there's a difference in controllability between the two. You can imagine if they're mixing internally, the liquid and the gas would then they would compete with one another. And so understanding how to tune that internal mix nozzle to your process is very important. Whereas on the external mix nozzle, the two are not in competition, meaning they won't fight each other to exit the orifice. Typically, you can have your liquid staying at a certain flow rate and pressure, and then you can adjust your air pressure on the outside, or your your air pressure, to then finally atomize that that liquid and to create a different drop size regime. And Kyle, in your experience in the lab, can you kind of share that internal mix and what the benefit would be for a client over an external mix? You know, why would they choose one over the other?
Yeah, because the gas and the liquid are meeting inside of the nozzle, you're typically going to have a more well-atomized spray and a more consistent droplet size and distribution as it leaves the nozzle. Now, whether you can actually interact those two inside the nozzle, if you've got a sticky substance or something, you're not going to want it to start to dry and stick inside the nozzle and clog it up, and so that's not going to be a real option. But internal mixes, the benefits is the force interaction between the gas and the air.
Yeah, and then going to that external mix, can you kind of describe where somebody might be looking at that, or what an operational benefit might be? You mentioned sticky substance and that kind of thing.
Yeah, the benefit of the external mix is, you know, the gas and the liquid are meeting outside the nozzle itself, right? And so then you can still achieve good atomization typically, but the atomization happens outside the nozzle, and the liquid stays purely liquid until it leaves the nozzle. And so you don't have any drying, any sticking, any gumming up of the liquid inside the nozzle itself. Also, like Justin mentioned with the internal, you have this balance between the operating pressure of the liquid and the gas. With an external mix, you can independently control the liquid and the gas streams, right? So you could potentially set your air pressure at some set amount, and then you can independently tune the liquid without affecting anything about what the gas is doing. Yeah. Similarly, if you set your liquid, you can then choose to increase your gas to maybe increase your atomization or something.
And you can effectively control drop size that way. So let's say you need a smaller drop for some reason, you have that capability of adjustment. And I've seen instances on the internal mix, let's say it's an SCR application where they use a lot of internal mix nozzles, but if there's a certain upset inside that pressure, it can actually vapor lock that nozzle, and you actually need a little bit more force to overcome to then start spraying. And so it's these little bitty insights that can go a long way, right? Getting environmental dings, because what we think a nozzle is flowing when in fact it's really not, is pretty important to know that you need to goose a little bit of that pressure to get it flowing again and then back it back down. But just understanding the mechanics of that can be very helpful. And then on the next slide, we're just going to have a kind of a neat visualization of these two fluid nozzles in action. This is actually our conference room in our lab out here in Texas using a FLIR camera, just to conceptualize how this fog, it's actually spraying a disinfectant in the room, how it can pretty quickly cover that area with that fine atomization. And so it's just a nice visual of what that small droplet can do, and then the velocity increase too with that two fluid atomization. So pretty neat to look at. The next piece is electrostatics. And again, getting our fluids where we need them to be for that transfer efficiency is very important, not only to be sustainable, but to make sure we're using the energy in a very good way. And Kyle, can you describe what we're seeing here? We noticed that we have these little solid stream nozzles and they're bending. What are we looking at here?
Right. So we want to look at two different types of electrostatic sprays. One is electrically assisted sprays, and this is where the liquid is charged, and as it leaves the nozzle, it is then drawn towards the target. Right. So this is great for like lubrication or anytime you have like an oil that could be actively charged. And so what you can see here is the liquid itself, as it leaves in a solid stream, is being drawn over towards that pipe. Right. We've positioned it so it's attracting it, but it's not able to actually hit the pipe. But imagine if you had a surface below or something where you wanted all of the liquid to transfer directly onto the target. By charging the liquid, you can accomplish that. And if you've got a passing chain for lubrication, for example, then a solid stream is best because it's just going to all land. You don't have little droplets that you're trying to manage as well. It's all sort of staying connected, which is nice. This is different than electrostatically atomized sprays, which I think we'll maybe touch on the next slide. Or one or two slides on. Okay, yeah. So here we have electrostatically assisted or ultrasonic sprays. So an ultrasonic spray is really the liquids coming through and being fed through I think they call it a horn that then vibrates at ultrasonic frequencies. And so that frequency can dictate the droplet size, and you can also have some shaping air to change the pattern shape as it leaves the nozzle.
And what's fascinating with these nozzles is you're able to get a very fine droplet with a tight distribution. And it's because of that piezoelectrics that's vibrating at a very high frequency. And that's what's giving you that primary breakup of that liquid. And you're going to see on our next slide kind of how fine that droplet is. And you can actually see it actually spraying in the lab. And a lot of times, these can be used in nano type applications, whether it be for producing nano electronics, nano wires, even lithium and battery technology, where deposition and
very fine droplets, very consistent droplet size.
Yeah, very important, particularly when you're spraying chemistries that could be thousands of dollars per ounce. This is very, very important to have that control. Now you can see on the right-hand side, we're leveraging that spray scan MPT technology and how much that liquid can be at the will of the atmosphere or the environment. Before we utilize that shaping air, it's just moving all over the place and seeing those eddy currents, and then we tighten it up at the end. And so just imagine not having that capability of controlling a liquid that is so costly to not be able to make it deposit where you need it to go. And Kyle, can you describe on this slide here on the right-hand side, what are we noticing or seeing as we adjust the parameters, like you mentioned on the horn of that ultrasonic nozzle, and then how we're getting everything to tighten up a bit?
Yeah, so it's a little hard to see, but you can see the nozzle itself in the top of the image there, and it has two little. You can see one, especially on the right-hand side, of shaping air, where there's air that comes out that pushes the fluid down towards the target, right? And so the atomization is happening due to the ultrasonic spray. So you're getting a nice fine droplet spray, a very uniform droplet size, not monodispersed, but a much tighter distribution than you'd see from a hydraulic spray or even a typical air atomized spray. And the spray down below, you can see how it looks like a fog almost. It's so small. And then on the right-hand side, you can see where that spray is going. You can see how susceptible these droplets are to any type of currents in the air that might be in a factory or in a process facility where you're going to use one of these nozzles. They're so small, they just move around, right? You can't really direct them towards the target, but by adding some shaping air and directing them towards that target, you can have a much more improved transfer efficiency to get them to the surface or through the process.
Yeah.
Yeah, that's great, guys. Before we move on to the instruments we use, we have a great question about two fluid atomizers. What's the pressure differential between the gas and the fluid that you recommend? And what do you recommend in terms of mass flow?
Yeah, mass flow, I would typically dictate by the process, right? You need a certain amount of material put down onto a target. You need a certain amount of fluid going through the process. Like usually the liquid mass flow is not something that we sort of independently determine. Unless, for example, we can't achieve good atomization, we might need to then use, say, 2 nozzles or more nozzles to pre-distribute the material through multiple nozzles or across a header. But the way we, what was that, Justin?
Oh, no, didn't say anything. Yep.
Oh, sorry.
No worries.
Yeah. So the typically way we would go about this is to put down a spray, and then it really depends on the nozzle type, I guess, typically.
Yeah, and the deltas too, you can span them. Like for an internal mix nozzle, the densities of the liquid versus the air is a bit different, and it just depends on your liquid. Typically, we can see a 10 liquid, 10 air differential, and if you get outside of those bands, you run the risk of vapor locking or having some kind of challenges within the process. But again, it definitely depends on the liquid that you're spraying, and that's where the lab testing, benchtop testing, really comes into very handy with what you're trying to achieve.
Yeah, that's great. We do have a follow-up from the question about amount of volume displaced also. So in the applications that this person's working with, they need to spray a very specific amount of milligrams over a surface in a specific amount of time. Is there a theoretical way to do this instead of taking samples from the nozzle every time that a variable changes, like pressure or temperature or whatever?
So the way we would approach this is, first and foremost, what is your transfer efficiency, right? Do you see a lot of spray going elsewhere, or do we have a reasonable expectation that the fluid that's leaving the nozzle is reaching the target and staying there? That's the first place to stand. And to assess that, at least in a trial case, you could spray into a target that could then be weighed. Given the flow rate, given the amount of time sprayed, how much material actually stayed with the target, or a surrogate target that would hold the material that you could take to the side and weigh. So assessing transfer efficiency is very important. And once you have an idea of the transfer efficiency, the percentage of sprayed material that reaches and stays with your target, then you can start to, again, go back to what is my overall flow rate, what's my conveyor speed, and calculate how much material will be landing across a given area or surface. And these are things we can optimize in the lab, or with that information, if that's something you have the facilities to do, then you could do.
Yeah, and there's some other instruments as well, like looking at the spray scan MBT, for example, in line at your process, is to be able to understand how that droplet is moving and how it vacillates with your pressure differentials, or even temperature. Temperature is huge. It can have a huge impact on your viscosities, which then impacts your spray pattern, the width, etc. So there's a number of ways to do it, but it is specific to your process, and those are the types of fuzzy challenges we like to work on for spray applications, for sure.
Yeah, that was good. Thanks, guys. Before we move on from electrostatic and ultrasonic too, how does droplet size, let's say 400 microns versus 100 microns, influence the droplets charging?
So what I'm going to do is, we actually have someone who went to grad school looking at electrostatically atomized sprays, so not necessarily charging to make them land on a surface without atomizing, but Paul Vesely went to, it's part of his grad school work, and then his design work in spraying systems has involved electrostatically atomized spray and charging those droplets specifically. So I'm going to message him on the side, and we can loop back to it if we have an answer from him during the talk here.
Yeah, that sounds great. All right, cool.
So we have a number of instruments at our disposal, and we'll kind of blaze through this piece a bit, but we have the tools to quantify how your sprays are moving. And then the key piece is translating that data into the process. So taking a good amount of that data and then saying, hey, where's the application of this? Where can we actually leverage this information? And that's where somebody like Kyle would take that research and that information, give it to the client, give it to the specialist such as myself, and then we can actually go out to your facility and say, hey, here's what we see in the lab, and bridge that chasm between that mind and machine piece and bring from the lab to production. And so we have our laser sheet imaging tool, we have our phase Doppler, we also have the PDPA, which is our phase Doppler and particle analyzer. And then we also have a fun one I like the most is that wind tunnel to see how those droplets are going to be impacted by various gas streams, you know, co-flow, counterflow, cross-flow. And combining all of those different instruments, we're able to glean some very powerful insights that that can then be leveraged in the field. And that's really what we enjoy doing and what we're highly equipped to empower you guys with the information to get some benefit.
Yeah, Spraying Systems has made, you know, huge investments in these types of facilities and instruments to bring these better solutions, more precise, more optimal, more sustainable solutions to our customers, right? So you're talking, you know, each of these systems might be the type of instrument that a professor at a university sort of hangs his hat on and says, you know, I use a phase Doppler to collect my data and really move my research forward, you know. And in outside Chicago alone, we have 3.5 of these types of instruments. So we have all of these tools, and there's a very comprehensive list on the website that we can provide a link later. But we have all these tools, so the benefit there is that we can use the best tool for the job, right? We can use the best instrument to provide us the data to then lead us towards the best solution.
Thanks, Kyle. And you know, with the experience that specifically you have had with all of these instruments, you've developed a tool that can then democratize some of this information and get it into the client's hands. And on the next slide, you're going to see we spoke a bit about it, you know, the spray scan MPT, and you know, the most beautiful engineering piece that we can see is something that's very, very simple, right? And Kyle did a great job of taking a highly complex system, such as drop size, and simplifying it to where it's consumable for our clients. And what you're seeing here, Kyle, I'll let you take the floor, but it's just fascinating technology.
Yeah, what we you know, this is so Justin referred to this, it's the spray scan MPT is what we call it. MPT is for mobile patternator. And so this allows a user to quickly and easily assess the distribution of a spray, right? This 2D distribution and leading to then the 1D distribution as well, like you can see on the bottom of the screen here. So the tool itself is something we've used in the lab for decades, the type of technology, but we've really compressed it into a user-friendly, simple is an oversimplification, but the goal is to make it very simple to use, right? There's a lot going on in the background that makes it user-friendly and fast. So in a matter of a minute from picking up the system, you can be looking at a result of a spray. This is a spray comparison tool that's then built in, so we can look at the changes of a spray, whether you're changing chemistries or you might be seeing a worn nozzle and you want to know or assess how worn is that nozzle and should I be replacing it. We try to make this very simple and easy where you can look at the changes of a spray over time to help with those types of decisions.
And where that's valuable is Kyle, you know, through the use of different technologies has boiled down, you know, between a healthy spray or assessing these sprays down to a simple number, you know, the correlation coefficient, and the implications that can have on your process in the field are very, very large. There's a particular application I can recall. A client was flowing through over 9,000 gallons per minute, and at a pretty good pressure. And just a small variance in the orifice or the flow rates, which was marginally detectable by their pumps, but could be noticed very quickly, preemptively by a spray scan, you would have the ability to see what that distribution does, but also that correlation coefficient between a healthy nozzle and what would be an unhealthy nozzle. And there's a number of places that this technology can be used for. And what you're seeing here is the ability to just have those unique insights. You know, the visual plots, a visualization tool. I really like the numerical tool, just that correlation coefficient. Say, here's a good nozzle, here's a bad nozzle. Are you at 90 or are you at 60? If you're at 60, it's time to replace, or whatever that threshold might be. And on the center line here, I just love this application to see the distribution for just a particular hand sprayer. You know, it's a very unique insight that, you know, in the past was not able to be gleaned. So, and then on the next slide, we're really kind of getting into why all of this matters and how does spray characterization lead to that innovation. And the big drivers that we see is the process optimization. And whenever you have the ability within your engineering group or with your team to speak the same language as it relates to spray characterization, there's a collective awareness of what's happening in your processes. And whenever you have that awareness, particularly as it relates to spray nozzles, then suddenly you find more and more opportunities. It's one of those things that the smaller you go, the bigger it gets. And that is definitely true with our spray technology. The other piece is driving that innovation is, you know, even with democratizing some of these tools like the Spray Scan MBT or various other drop analysis tools, it's a big driver for innovation. You get another layer that was never a discussion point in the past for various processes, whether it's conveyor, coating, quenching, all of those things, and that leads itself to more innovative way of looking at your process and any of those challenges. And then, of course, that sustainability initiative is huge. Transfer efficiency, like Kyle mentioned, if we're not getting 100% transfer efficiency, we have a huge amount of opportunity. And Kyle, in your experience, have you ever seen an application with a pure 100% transfer efficiency with atomized sprays and that aspect?
Electrostatic charging of droplets certainly helps with that. You can think of, you know, paint sprays on, you know, where they charge the droplets and everything onto the surface of the car, right? But besides that, you're typically going to lose at least some, even a low percentage of the droplets, and potentially a high percentage depending on how things are set up, right? Those fine droplets tend to get swept away, whereas larger droplets will go where you intend. But the larger droplets won't necessarily coat as uniformly, right? So there's typically a balance there that we have to kind of try to achieve. I know the time's getting a little short, Justin. I'm not sure if we've got a couple slides here we wanted to hit on before we run a little towards the end of our hour.
Before we move on, can we talk a little bit, can we help test particular slurries to decide what nozzle is best to use in a particular application?
Yeah, the answer to there is yes. Yeah, so we can test in our laboratory with different types of materials. That does depend on the flammability and the hazardous nature of the material. So the easiest way there is to get in touch with us, and we can help to sort of do a preliminary review of an MSDS or material and help to make that decision. And if we cannot bring a material in, sometimes we have ways of helping to determine a suitable surrogate, so we can do something representative even though it might not be the actual material.
All right, perfect. We'll just run through some applications and then hit home. Sound good?
Yeah, Mary, go ahead and go to slide 26 on the coverage distribution piece, if you would. And we can go one more slide.
Okay, sounds good.
So we were talking about transfer efficiency, and if you look on this left-hand corner, you've got the bounce back. This is where Kyle and his team can be very, very helpful while we're using some pulse width modulation and some neat technology here to get some good coating. There's still opportunity for mitigating some of that bounce back and enhancing that transfer efficiency. And then, Mary, we can go to the next slide. The other piece too is our drop size applications in pharmaceuticals. You know, the ability to, you know, we mentioned slurries, perhaps y'all are working with spray dry and that aspect. We can absolutely assist with that piece, enhancing the amount of active that is being utilized. And also with our fluid air division, we can use electrostatics to reduce that temperature to make sure that we're not impacting any of your biologics that are flowing through our nozzles. And then on the next one too, we do have that capability for the CFD side of things, the computational fluid dynamics, to understand where the droplets are going and processes that might be a bit too dangerous to physically observe. And what's nice is we can validate this information, this data, with actual lab data, and then use that to inform our CFD models. Very good piece for us to leverage. And then moving on to our next to last slide. So why all of this information matters on the drop size is whoever has the data wins, and we're determined to democratize spray data, get it into your hands in a way that you guys can leverage that information. And then Kyle, on our last slide here, Mary, if you can go one more. You know, we looked at our drop size, our spray pattern and shape, our spray angle and velocity, and our spray impact. We really appreciate all the time that you guys spent, and we're happy to hang around for some other questions. If there's anything out there, we're more than available to talk specific applications and help you guys out.
We have a good one here. So I'm having problems spraying oil with a flat fan PWM nozzle. I have kind of a full spray pattern, but with gross lines at the sides of the pattern. What can I do to minimize this? Increase pressure? Could it be viscosity? Any other thoughts?
Yeah, so we refer to this as heavy edges, and a lot of times either high viscosity or high surface tension sprays can have this. And so increasing the temperature to reduce those properties could be beneficial. We could go to more of an air atomizing nozzle, or sometimes it can be difficult to ahead of time decide what nozzle or what nozzle technology is going to make a spray improve. And at that point, it's typically easiest to bring it into our lab, some of the material, and try spraying it with a few different options rather than sending nozzles back and forth and doing all this. So that's a large reason why we have the lab. You know, it's at everyone's disposal. Typically, we will discuss a project, come up with a cost as a contract-based testing service. When we do bring things in or do something very specific for a specific client, it's all, you know, kept confidential and everything, and you're left with a very specific answer. So a flat fan with a PWM nozzle, if you have something that's a bit viscous, it can be difficult to overcome that sometimes. Those heavy edges, sometimes you end up with sort of not only heavy edges, but then a bit of a concentration in the center, you know, and it might be necessary to heat that material up or something.
And two, on the PWM, if you've got, depending on your duty cycle, you know, you can adjust your on and off time. If you're pulsing at a high frequency, you know, you're going to kind of chop that spray a little bit and have some other issues there, to where if we can increase your flow rate a little bit at each instance, but adjust your on and off time, that's another opportunity to help alleviate and adjust that spray. But it does sound to me that there's a viscosity challenge there and some temperature challenges that might be able to get mitigated, particularly now if it's just now arising. If you have cooler temperatures, we see that a lot in these plants. You know, oh, it ran great, you know, during the summer we had no QA/QC issues, and then you get to the winter time and suddenly everything's just not functioning, and that temperature can have a large impact on your process. That's a great question.
Mm-hmm. Mm-hmm.
Okay, we got one more. What is your standard turn down ratio for nozzles, and how does it change with respect to nozzle style?
So yeah, it really depends on nozzle type. We do have certain specific nozzle styles that are designed to accommodate larger turn down ratio. Obviously, hydraulic sprays, you know, where your pressure is dictating your flow rate through your nozzle. As you start to change the pressure or change the flow rate, you're going to change the pressure naturally, right? And so then you're going to change the atomization characteristics and the distribution. If we're looking at air atomizing nozzles, you have quite a bit more, you know, room to move things around, especially with an external air atomized nozzle. You can change, like we said, you can change that liquid flow rate and maintain the air or adjust the air independently to maintain a good spray. We do have what we call FlowMax. Our FlowMax line of nozzles is designed to accommodate a 10-to-1 turn down ratio. So I would think any other nozzle you're dealing with is certainly less than that, because
Yeah.
that's specifically designed to be good at that. But it really depends on what you can allow to change as you start to change the scale of your process. Yeah. And you might need to physically change the nozzle. Yeah. Go ahead, Justin.
Yeah, from a turn down perspective, you're typically what you see is like a 5-to-1. Again, it is dependent, and like Kyle said, the flow max can handle that 10-to-1. And depending on your process, it's a function of the number of nozzles as well. I think of it, you turn it on and off based off of your needs. Once you max out the turn down ratio of one nozzle, then typically you're going to have to put another one in to handle your upsets or, your max and min conditions. But that's a great question. So in short, usually for, 2 fluid, we'll see a 5-to-1 ratio, and then our flow max nozzles right at 10-to-1. But again, it depends on your drop size requirements, your flow rates. It's very, very specific to your application, but we're happy to look into that a bit further too.
Mm-hmm.
All right, looks like we have a good answer. Just to refresh everyone of the question earlier on electrostatic ultrasonic nozzles, how does droplet size, for example, 400 microns versus 100 microns, influence droplets charging?
Yeah, so I spoke with Paul in the chat here, and he's let me know that typically smaller droplets would carry a higher charge to mass. So the smaller droplets, the mass to charge ratio, you're going to have a higher charge concentration in small droplets. He said typically if you're looking for a more uniform charge, then you want to go to lower or smaller orifices and smaller droplets, which will tend to sort of compress those parameters together. But if you want more detail on that, certainly reach out to any of us three, and we can get you in contact with Paul or somebody else to have a direct conversation, get some good answers there. I'm pretending I know. Thank you, Paul.
All right, guys, that's great. We have no more open questions for now. If you guys have any questions that pop up, please feel free to email us at spray.analysis@spray.com, and we'll be sure to answer your questions. Thanks, Kyle. Thanks, Justin. Appreciate all your insights today.
Yep. Thanks so much, Mary.
Thanks, Mary.
Kyle.
Yeah.
Bye-bye.